Alrighty, welcome everybody. Before we even get going with introductions, the first thing we're going to do here in the Reactor real-world demo is put a liter of water on the new MSR Reactor stove system. We're going to put a liter of water on our most popular stove, the Pocket Rocket right here. We're going to get both of those on their way to a boil, and then we're going to begin with the it slices, it dices. It's a one-time limited availability. Give you the whole song and dance. So Drew's going to light up the reactor. I'll light up the Pocket Rocket. The first thing you're going to notice here is the Pocket Rocket has what you're used to, kind of a conventional MSR blue flame that we see on most backcountry camping stoves. The MSR Reactor has a burner and a flame that looks uniquely different, and we will get into the technology in that in just a second. But I do want to point out we never miss an opportunity for a brand hint. All right, my name's John Almquist. I'm the brand manager for MSR. Drew Keegan is the product manager for our entire stove, fuel, and cookware line, and has been certainly one of the champions kind of driving the Reactor project forward. Something we've been working on for more than 2 years, and we're pretty excited to finally be able to kind of sit up here in front of everybody and introduce it at the Summer 06 Outdoor Retailer Show. The impetus behind the Reactor project was to take what we consider to be revolutionary advancement in stove technology basically to a new level. And the challenge that manufacturers, including MSR, have been trying to overcome in recent years is to take performance specifications, boil times, and efficiencies that you get in controlled test conditions. And those are the specs that you read whether you pick up our workbook or a competitor's workbook or look on websites, look at packaging. All those specs that you see there, boil times and efficiencies, those numbers are generated in controlled test environments. The challenge has really been to take those specifications and make them hold up out in the real world environment. And anybody that's used a conventional canister stove or canister stove system knows that what you read on this paper is not always what you experience while you're backcountry camping. And in order to make that jump, that revolutionary change in technology, we had to think outside the box a little bit, think beyond what we've been considering standard kind of conventional stove technology, and bring some new technology into the backcountry stove market. And that was the real challenge, and that's what took a couple of years. I'm going to go ahead and pass the microphone over to Drew Keegan here.
So this is everything you would need to cook right here. It's a very rattle-free system. Everything's tightly packed inside. You have a locking latch mechanism on the top to keep the lid down. Undo that and unfold it, and it's your pot handle. You have a polycarbonate, like a Lexan lid, that's very heat resistant and durable. 8-ounce canister of fuel fits inside the system. The stove body itself, and a piece of pack towel to kind of protect the two components and aid in cleanup once you're done cooking. So getting into the technology, the first thing you'll notice with this system is the heat exchanger fins on the bottom of the pot. These fins are actually an integral portion of the upper part of the pot. It kind of starts out as a hockey disc, or a hockey puck rather, of aluminum, kind of a large disc that's impact extruded. So the fins in the top portion of the pot are all formed at the same time. Then we take another piece of aluminum, this darker piece that you see here, that's a heat exchanger shroud that we add secondarily and weld that around the perimeter of the pot as well as to each of the fins. It means we have great thermal conductivity through both components of the heat exchanger system. So what the heat exchanger does for you in the typical mode of heat transfer, which is convection, the hot exhaust gases are heating the cookware. The heat exchanger is going to increase the surface area. Just want to stop for a second and point out that we've got 1 liter of water with the...
Somebody step forward, please.
The reactor.
Stick your finger in there. See how warm that is. Yeah, really.
We've got barely bath water temperature in the Pocket Rocket system. So getting back to the heat exchanger, this system also does something else that's kind of different. We have forced convection. Basically, we're enabling the stove system to transfer all of the heat very effectively into the cookware. The kind of revolutionary thing that John was talking about, though, is that we have a radiant burner in this stove. So as you saw when we lit up the stove, or in this giant photo behind me, a radiant burner is a second mode of heat transfer to this stove. So much like the sun on a cold winter day can heat your face up without heating up the air around you, and it doesn't matter that it's windy, that radiant heat is doing the same thing in this stove system. It's directed right at the bottom of the pot. So again, the increased surface area of the heat exchanger fins and the dark color of the hard anodized aluminum is going to absorb all of that radiant heat transfer. Talking about the stove, the radiant burner is not the mesh screen that you see above or see in the photo behind me, but it's actually a porous metal foam that's below that. So it's much like a metal sponge, and that's a proprietary alloy that we've worked on with a company here in the US. What that allows us to do is do 100% primary air entrainment. And to explain that a little further, when you look at a traditional burner technology stove like the Superfly here, you entrain about 60% of the air required for combustion in through the mixer tube. Then you need some space, and that's why the pot supports lift the pot up a ways off the burner head, is that you need air to be accessible to the top of the burner head to complete combustion. With the reactor stove system, we can entrain 100% of the air required to complete combustion in through the side of the stove. And therefore we can put the pot and heat exchanger system right down onto the burner head and totally enclose that. So now any wind that's going to come across the system has no chance of blowing heat away from the cookware. The last thing I want to point out is this small aluminum disc that you see here. There's an internal pressure regulator behind there. And what that's doing for us is that when you take a standard canister at room temperature and it's full, it's about 65 psi. As you have phase change from liquid to vapor, or you have the fuel level decline or cold environmental conditions, the pressure inside the canister is going to decrease. So with using a pressure regulator, we can set up the stove to run optimally as if the canister was almost empty, which might be, like I said, 10 or 15 psi. The stove is running at a maximum output of around 12.5 psi. Yeah, all the other stoves, really all of our stoves and our competition are tuned when the canister is at its full and warm condition, so they're tuned for that full 65 psi. What that means when you put the whole system together is that you have a very fast and very efficient system. With the reactor, you can boil around 22 liters of water on one 8-ounce canister. In comparison, something like the Superfly or the Pocket Rocket that you see here are only going to boil around 16 liters of water. What's maybe more impressive than that, though, is that the first liter of water with the reactor system is around a 3-minute boil time. That 22nd liter is going to be around a 3.5-minute boil time. So it's very consistent performance throughout the life of the canister. And again, comparing that to other stoves like the Superfly or Pocket Rocket, on those first liters with those stoves, you might see a 3.5 minute boil time. But with every liter after that, the boil times are going to get longer and longer. So by the time you get to the 10th or 12th or 15th liter of water, you might be at 7 or 8 minute boil times. And there's certainly some product on the market that's going to fail to boil water when it gets to very low canister levels. So you end up with half-empty canisters. I know I have lots of those on my basement shelf. This stove, you can feel really good about going out for a weekend with a half-empty canister and know you're going to get great performance out of the stove and be able to use all the fuel until it's entirely gone. With that, I'll hand it back over to John.
I'm just going to elaborate a little bit on some of the numbers Drew talked about. Being an engineer, he's really excited about the numbers you see on this page right here. Kind of those performance specs done in controlled laboratory conditions. And at MSR, we test the heck out of our stoves. There's the next liter of water. If somebody wants to come up and go ahead and see how warm this water is. You wouldn't take a bath in there, would you? Yeah. The real advantage of the Pocket Rocket is not that it has really good specs in those controlled lab test conditions. Drew talked about some of those fantastic specs. One was fast boil times. Basically 3 minutes or just under 3 minutes for that first liter of water. And that last liter of water which is 22 liters later, assuming you're using an 8-ounce canister of fuel, boils in about 3.5 minutes. That's better than most other stoves or stove systems on the market, certainly. But what really sets the reactor stove system apart is the ability to carry those specs from those controlled test lab conditions out into the real world. We have a 3-minute boil time here. If we were to go outside, you'd find the boil time very similar. We have fantastic efficiencies, boiling almost, or actually just over, 22 liters of water on an 8-ounce canister. If you go up out into the Alpine, you're going to find very similar efficiencies. There's a lot of other stoves that have fantastic boil times. There's a lot of other stove systems that now have very similar laboratory efficiencies as the reactor, boiling in the low to mid 20s of liters of water on one 8-ounce canister. But what happens when you take them out of those controlled test conditions and put them in conditions where we actually go camping, their boil times are increased, which is not good. They go from maybe 4 minutes to 6 minutes to 8 minutes, that although their combustion rate doesn't specifically change, you have to leave the pot on the burning stove so much longer just to bring your water to boil that you end up burning a lot more fuel. So what we've done here is a quick attempt to kind of replicate real-world conditions that we camp in inside. We'd all rather be outside up in the Wasatch somewhere beside some lingering late summer snowfield with a cool breeze, but we're working. So instead, we brought in a bit of a breeze. .3 miles per hour. Not significant, but it is a breeze. And we've also brought these canisters below room temperature. We have them sitting in some cold ice water here. Now that's not as cold as the canister would be on a cool morning when you started burning it and the evaporative cooling caused some frost around the outside. But at least it's cooled below room temperature, so they're not running at full pressure. And what you're seeing is the reactor is still performing like it does in the lab conditions, whereas other very good performing stoves decrease that performance significantly. What I'm going to do now is take the pocket rocket out of the wind to give it as much advantage as it can. But before we do that, the one thing that's kind of an interesting demonstration is to come up and put your hand on the downwind side of both of these setups. Your hand on the downwind side of the reactor stove system, you feel very little heat loss coming off the back side. If you put your hand on the downwind side of the pocket rocket, you feel significant warmth being lost. So anybody wants to try that, step on up. Feel the difference? Yeah, very noticeable. With that, I'll balance this. Take that out of the wind. So now we've taken the wind out of the equation for the pocket rocket. We're still leaving it on the reactor. We'll be able to boil a whole nother liter of water here before we bring this liter of water to boil in the pocket rocket. Any questions?